getting something wrong here? I'm going to be able to take this M and place it up here in the E. Oh yeah, so what happened is I can say that this is actually, so I can use this inequality to go from here to here, so I can pretend this was taken to the power M, but then also divided by the power M, and this is basically e to the minus 1 taken to this over. So it takes you a while to get used to this, but you can use this inequality to go from here to here, and then this is a bit more understandable. Okay? All right, so my goal again is to derive this inequality here. So let's break this down into parts. 1 minus 1 over m. This is the probability that any bit is not set. Right? And if I do this k to the raised to the power k, then when I put in any item in the hash function, any item into the Bloom filter, this is the probability that a bit is not set by one item. So let's say bit vi not set by some x. Right? So is this clear? This is the probability any one bit is not set because there are n bits. It's chosen it randomly. I do it k times. The hash functions are independent. So probability any one bit is not set. And now I'm going to do this for n elements. How many? I'm putting n elements into here. And so by putting n elements in, I'm going to actually get this. So after I put in n elements, so probability that after n elements, that some bit is not set. So the probability a bit is not set after putting in n elements. So now I want to say, so this tells me some property about the Bloom filter after I put in n elements. This is for any bit, the probability that's not set. So now I want to go and check if some other object is in there, right? Some object which is actually not put in my Bloom filter. So I'm going to check each bit. So I'm going to check k bits, and it's only a false positive if all of them are set. If all of them are set to 1. And I need to do this k times. So I need to look at, so the probability that, so 1 minus this quantity, 1 minus this quantity is the probability that one of the bits is set. Okay? This is the probability that a bit is set after I put in n items. And I need to do this k times. So this is the probability that I check k independent hash functions and all of the bits are set to 1, even though the item wasn't in there. Okay, so that's how I derive this property. So and if you get something where like the number of bits for items is like 5, so you have 5 bits for every item you get in there, then you get really pretty small probabilities. So that means that this becomes about 5 times log 2 is like 6 or 7. You know, maybe you want to get this quantity k to be 10. You can get 10 hash functions, and you kind of, and m over n log 2 is basically k. Then then you're going to get a very small probability of collision. Right? So you kind of want to try and abide by this equation and allocate, maybe get 10 hash functions, and then allocate how many bits you need based on how many items you have. Somehow play around with this kind of rough relationship. And this works really well. Cisco, all sorts of, Cisco and their routers, all sorts of places use these bloom filters for very quickly doing these things. And there's a way you can kind of use this to speed up some of the later rounds of this a priori algorithm as well. All right, great. So next week we'll start on regression, and on Monday I'm going to kind of give an overview of all of the following lectures and trying to kind of put them all in perspective of what we can do with regression. And then we'll dive into several topics, the 4 lectures after that.